Welcome to our discussion of hypothesis testing. So, yesterday we were discussing the theory behind the hypothesis testing, right? What is the actual procedure, what is the statistical mechanism behind the hypothesis testing that we are discussing yesterday. Now, today what we will do, we will re-estimate our income consumption model, and then we will see whether you can apply our knowledge of hypothesis testing to interpret the results that Stata is giving to us, right. So, we will re-estimate the model once again. Now, if we go back to our data set and do the estimation, this is our result. Look at the result. Okay. So, we have estimated a consumption function and we have only one explanatory variable income, and the coefficient of income is 0.5090. That means, for a unit change in income, on an average consumption changes by 0.5090 unit. Okay. This is the interpretation that we have learned, but now what we will do? We will see whether this particular income coefficient it is statistically significant or not, right. It is statistically significant or not, and by checking the statistical significance, basically we are ensuring that the value what we got here is not by a chance factor, rather it is due to a statistical significance, right. Now, how will you do that? If you go back to our discussion yesterday, then we said that what is the decision rule of hypothesis testing? The decision rule says that we have to first construct the T-statistic, and that is beta hat divided by standard error of beta hat. Okay. And in this particular case, if you look at what is our beta hat? Beta hat is 0.5090, and what is the standard error? Standard error is 0.035. So, 0.5090 divided by 0.0357. 0357. If you do that, then what you will get? You will get the calculated value of the T, which is supplied by Stata, 14.24. Okay, 14.24. So, this is the calculated value. Okay, this is the calculated value, and this calculated value we have to compare with the tabulated value, right. That is what we learned. That means, basically in terms of the diagram, what is our calculated value? Calculated value is 14.24. Now, we want to know what is the tabulated value. That means, what is this value? This is called tabulated value. And if you look at your T table and specify your alpha, that means this area is what we said, that 2.5%, this is also 2.5%. That means, we said that alpha equals to 5%, or it is equal to 0.05, right. Let us specify the area, the size of the critical region. Size of the critical region is 5%. So, that means, I am saying that alpha is equals to, I am saying size of the critical region, or we can also say that this is called probability probability of committing type 1 error or level of significance. These are the three interpretation of alpha, and that is equals to 5%, right, 5%. So, that means we are saying that we will commit 5 type 1 errors in 100 cases, right. That is the pre-specified level of alpha we have kept. Now, if you go back to your table and see the value of t, calculated value of t at a specific, sorry, this is, yeah. So, if you look at your table, now here you see that total number of observation is 10, and as I said yesterday, the t will follow n minus 2 degrees of freedom, that means 8 degrees of freedom. So, what you have to see, at 8 degrees of freedom and 5% level of significance, what is the value of t? Okay, what is the value of t? So, that means this is equals to, I will say this is equals to 2.306 at alpha equals to 5% and degrees of freedom equals to 8. At 8 degrees of freedom, this is 2.306. Now, when your calculated value is 14.24 and the tabulated value is only 2.306, you can understand that means you are actually easily entering into the critical region. Okay, you are actually entering into the critical region. So, that means what I said, that calculated t, so t calculated, which is 14.24, is actually greater than t tabulated, which is 2.306. And even at the 1% level also, you will see that your calculated value is greater than the tabulated one, that you can verify from the t table. So, that means this implies that reject your null hypothesis, reject H naught. And what is our H naught we mentioned? H naught was beta equals to 0. That means income does not have any impact on consumption. Okay? Income does not have any impact on consumption. Now, from this diagram, if you reject your H naught, so that means we are actually we can establish our claim that yes, income has significant impact on consumption. From the diagram, one thing is very clear, if a particular variable is significant at 5%, will it be significant at 10%? The answer is yes, because if you increase the size of this critical region, then obviously it would be easier for you to enter into the critical region, right. The more you increase, more you have about the size of the critical region, it would become easier for the calculated value to enter into the critical region. If I reverse the question, if the variable is significant at 5%, will it be significant at 1% also? That we may not say anything about, that we have to check, because if you reduce the size of the critical region, then there is the calculated value may or may not enter into the critical region. It is very simple, right? You increase the size, it is become easier for calculated value to enter. If you reduce the size, then it would be difficult for the calculated value to enter into the critical region. So, once the variable is significant at a specified level, that means it will be automatically significant at a higher level of significance also. A variable which is significant at 5%, it is definitely significant at 10%. But if the variable is significant at 5%, it may or may not significant at 1%. That we have to again check. That you have to keep in mind. So, this area we said that this is the area of non-rejection and this is the area of rejection which is called the critical region. critical region, level of significance and probability of committing type 1 error. All these are related concepts. When I am specifying alpha equals to 5, that means probability of committing type 1 error is actually 0.05. That means out of 100 cases, you are actually committing your type 1 error 5 times. Okay. Now, this is what we can learn. So, that means if you want to take the decision based on the T statistic, what you have to do? You have to take the calculated value, you have to compare with the tabulated value, and based on whether your calculated value is greater than the tabulated one or not, you have to decide whether to reject your null or not. But this Stata has made our life simple by supplying an additional information. What is that additional information? That additional information is here. Look at, they have also given something called P. What is this P? Now, you have to keep in mind that this P, what Stata has given as P is actually called exact level of significance. Or you can say that this is the exact number of type 1 error. Now, why this P is required? As I said, this T is telling that this is significant at 5%, but I do not know whether it is significant at 1% level also. I need to again check the value of T at 1% level and then decide. But if you take P, since this is called exact level of significance, that means I exactly know the size of the critical region, right? And if you go by the P value, then you need not, you do not have to compare the tabulated with the calculated one. Rather, what you know, if the value of P is, let us say in this case, what is the value of P? 0.000. That means you are actually not committing type 1 error at all. But then, as I said earlier, when your decision making involves some kind of probability distribution, because it is T divided by standard error of beta hat divided by standard error of beta hat, that determine your T. So, that means probability distribution is involved there. How is it possible that you are not committing any type 1 error? Actually, the meaning of this is the P value is very small, 0.000000000, some value will come. It is such a small value that Stata is reporting it as 0. So, that means in 100 cases you may not commit any mistake, maybe in 1000 cases something like that, okay, something like that. So, probability of committing type 1 error is very small when your P value is small, right. So, based on the P value, statistician or econometrician, they have made a simple rule. What is the rule? You have to multiply the P value with 100. And if after multiplication, if this becomes less than 1, then we will say that the variable is significant at 1%. Okay? Then you multiply this by 100, and if this becomes greater than 1 but less than 5, then we will say that the variable is significant at 5%. And if the variable P value after multiplication, if it is greater than 5 but less than 10, then we will say that this is the variable is significant at 10%. And if after multiplication, if it is greater than 10, then we will say that the variable is actually insignificant. Okay, insignificant. For example, let us say the P value is, for example, let us say P value is 0.12. So, if you multiply that by 100, that means P multiplied by 100 would be equals to 12. Okay. So, that means out of 100 cases you are committing 12 type 1 errors, and as I said earlier, we cannot afford of making 12 errors, more than 10 errors we cannot afford to make, then we will say that the variable is actually insignificant. So, this simple rule, if you remember, just take the p value, lower the p value, higher would be the level of significance. Just multiply that by 100 and follow this simple rule. Okay? Follow this simple rule. Because we do not report the result while interpreting, we do not say the variable is significant at 2.3% or 4.5% or 1.2%, nothing like that. We will only say whether it is significant at 1%, 5% or 10%. That means all this exact level of significance will be converted into 1%, 5% and 10% after multiplying this by 100. If it is less than 1, then it is significant at 1%. If it is less than 5 but greater than 1, then significant at 5%. Greater than 5 but less than 10, it is significant at 10% only. And after multiplication, if it is greater than 10, then we will say that this is insignificant actually. Okay. This is the simple rule that we apply to see whether the variable is significant following the comparing t with the tabulated one and applying this p. So, this is called level of significance approach. But there is an alternative way of checking the significance of the variable, that is called the interval approach, confidence interval approach. Okay? Confidence interval approach. So, confidence interval approach of checking the significance Now, what I said, when you are estimating this type of model y equals to alpha plus beta x I plus u I, and your hypothesis, null hypothesis is beta equals to 0, that means hypothesized value of the true population parameter is 0, then in interval approach what you have to do, you have to just check, let us say this is in this interval approach, this 1 minus alpha, this region, whether this region captures, whether this region, this particular interval, that means this is called region of confidence or region of non-rejection. So, whether the hypothesized value of the true population parameter is captured by this interval or not. So, what we have to check, whether this interval captures captures the hypothesized value of the true population parameter. Or not. And how this interval is determined? The interval is determined as beta hat plus minus t alpha by 2 into standard error of beta hat, right. So, that means from this particular example, what is beta hat? Beta hat is 0.5090 and standard error is 0.0357, and the calculated value of t is 2.36. If you put all these values, that means the upper limit, this is called lower limit of the interval, lower limit, and this is called upper limit. So, that means lower limit of the interval equals to 0.5090 plus what is T alpha by 2? 2.306, and what is standard error of beta hat? That is basically 0.0357. If you do that, then you will get the lower limit of the interval, and that is actually given by Stata. What is the value? Look at this. Stata has given you 95% confidence interval. That means Stata have specified alpha equals to 5. What is the value? Value is 0.4266. This would become 0.4266. That is the lower limit of the interval. What would be the upper limit of the interval? Upper limit of the interval would be beta hat, sorry, this is actually, I have, this is minus, beta hat minus this, and upper limit would be beta hat plus this 0.5090 plus 2.306 multiplied by 0.0357, and that would become your upper limit, which is 0.5915, 0.5915. Okay. This is how the interval, confidence interval is constructed using this particular formula. One thing you have to keep in mind, Stata will always give you the confidence interval specifying alpha equals to 5%. That means this is 95% confidence interval. If you would like to get confidence interval specifying alpha equals to 1% or alpha equals to 10%, that means 90% and 99% confidence interval you can always calculate manually. Stata will not give you. Stata will give you only one single interval, that is called 95% confidence interval. And calculating 99% or 90% confidence interval is very easy. Instead of 2.306, you have to specify t value at 1% and 10%. That is all. Okay, that is all. So, this is how the interval is constructed, and as I said earlier, the standard error determines the size of the region. That means the width range of this interval is determined by the beta hat, because beta hat is constant, fixed, T alpha by 2 is also fixed for a given number of observation, but depending on the standard error of beta hat, this particular size or region of non-rejection, or this is called region of non-rejection, okay, that is actually determined by your standard error of beta hat. Higher the standard error, higher would be this size, and if this size is higher, so obviously it would be highly probable that each and every hypothesized value of the true population will be captured by this interval. If your size of the interval is much wider, a wide range, wide size, a much wider interval will automatically capture the true hypothesized value. That is not a great deal. So, that means your decision making would be precise if your standard error is precise. That is why while estimating the model, one of our desirable property we said that should be the minimum variance property should be there, because if the variance is minimum, standard error is minimum, then your interval would also become very precise. Higher the size of the interval, larger the size of the interval, less would be the preciseness in your decision making. That we have to keep in mind. This is how you construct your interval. Then what is the decision rule? Decision rule says, if interval, if the estimated confidence interval captures the hypothesized value of the true population parameter okay, if the hypothesized value of the true population parameter is captured by the interval, then the decision making rule says you do not reject your null. Okay, what I am saying, you do not reject your null. Okay. So, if your true value, if your hypothesized value of the true population parameter is captured by this interval, then the decision making rule says you should not, you do not reject your null. And if you do not reject your null, then what would be your decision? That means what would be the inference? That means variable is not significant. That means a variable is not significant. This is the decision making rule. Okay. Now, in this particular case, look at what is happening. What is the interval? 0.4266 and 0.5090. Now, in this interval, do you think the true hypothesized value is captured? Is 0 captured by this interval? 0.42 to 0.59. Since it is in the positive axis, you can understand that 0 is not captured. And if 0 is not captured by your estimated interval, then you have to reject your null. Okay? You have to reject your null. And if you reject your null, that means variable is significant. So, that means we can say that whether you follow level of significance approach or interval estimation approach, both these approaches are leading to same result. It should not so happen that a variable is significant when you follow the confidence interval approach, but it is otherwise when you follow the level of significance approach. That means you are comparing calculated t with the tabulated t, it should not so happen. Okay. All right. So, what we are saying then? So, that means population parameter, if the estimated confidence interval captures the hypothesized value of the true population parameter, then the decision is do not reject your null. H naught. And if interval, if it is not captured, by the interval, then reject H naught. and that is what is happening in this particular case. Okay. So, that means 0 does not lie between 0.42 and 0.59. So, that means here it is 0.42 and here it is 0.59. So, 0 is not there in this interval, 0 lies outside the interval. So, we are rejecting the null and claiming that income does have significant impact on consumption. Now, one more thing what we have to remember, we said that the interval is estimated using this formula beta hat plus minus standard error T alpha by 2 into standard error of beta hat. Now, sometimes by mistake what we do, we estimate the interval and we see whether this beta hat is actually lying in this interval or not. For example, here after estimating the interval, you will see that your beta hat 0.50 is lying in the interval, and as I said, decision making rule says when the interval captures the value, then you do not reject your null, and if you do not reject your null, then your variable would be insignificant. But that is actually not the case by level of significance approach. Your T says variable is significant. That is a mistake. We should never examine whether this beta hat is actually lying in the interval or not. Rather, what I said, beta hat will only play a role in the construction of the interval. Once the interval is constructed, we will only see whether the hypothesized value of the population parameter is lying here or not. And what is the hypothesized value? Beta equals to 0. So, we will always see whether 0 is lying here or not this beta hat. That is one thing. And secondly, since beta hat, standard error of beta hat is playing a role there, we must also know how is the standard error calculated. See, standard error of beta hat is basically root of variance of beta hat. And how is this variance of beta hat calculated? Variance of beta hat is calculated using this formula, sigma square divided by standard xi square. And what is sigma square? Sigma square is basically variance of ui, and summation xi square is basically sum of xi minus x bar whole square. But this sigma square is actually unknown to you. Sigma square is an unknown population parameter. So, if sigma square is unknown, then how do you calculate variance of beta hat and standard error of beta hat? In that context, we have to keep in mind that when something is unknown in statistics or econometrics, statisticians they say that you replace the unknown population parameter with its sample counterpart. Since sigma square is unknown, then what you do? You calculate your variance of beta hat using its sample counterpart, which is basically sigma hat square divided by summation xi square. And what is sigma hat square? Sigma hat square is basically summation ui hat square divided by its degrees of freedom. That means sigma hat square is nothing but your residual sum of square. Residual sum of square, and what is the degrees of freedom? It is n minus k, where k is the total number of parameter to be estimated including the intercept, where k is the total number of parameter including the intercept. That is how you calculate your sigma hat square, and that is how you calculate your variance of beta hat. And why the degrees of freedom for RSS is n minus k, that we have discussed in our previous class when we were talking about the ANOVA table. Okay? We discussed, if you go back to our previous lecture, to that particular section we have clearly explained what is the degrees of freedom for TSS, what is the degrees of freedom for RSS, and what is the degrees of freedom for ESS. So, that means one thing we have learned here, when we have a problem with unknown population parameter while computing some statistical measure, our rule says we have to replace that with the untrue with the sample counterpart. Sigma square is unknown, so we are replacing by sigma hat square, which is nothing but summation ui hat square or RSS by its degrees of freedom. So, this is how you can actually work with your hypothesis testing. So far we discussed the estimation and hypothesis testing in the context of a 2 variable linear regression model. That means we have only one explanatory variable in the right hand side. Now, what will happen when there are multiple explanatory variables in the right hand side? That we will discuss in our next class. So, in our next class we will talk about multiple linear regression model. Thank you.